Bismillahirrahmanirrahim. Assalamu alaikum. In last class, we discussed about the proof of Wilson's theorem. So today we will discuss Fermat's little theorem. So before going to that, let me introduce least residues. Okay. For example, let we have p equals 7 is a prime number and a equals 12. Clearly, p does not divide a. Okay. Now, if you look at the product of natural number with a, and we divide that number by 7. Okay, so we need to find the modulo 7. For example, 1 times 12 is, so if we divide 12 by 7, we get remainder 5. Okay, then 2 times 12 is 24. So when 24 is divided by 7, then the remainder is 3. And then 3 times 12, which is 36. When 36 is divided by 7, then the remainder is 1. Okay. Then 4 times 12 is divided by 7, then the remainder is 6. Modulo 7, and then 5 times 12. So this is again 4 modulo 7, and then 6 times 12 is congruent to 2 modulo 7. And when we increase number, for example, 7 times 12, so 7 times 12 again gives you 5 modulo 7, which is same as 1 times 12 or 7 times 12. Okay. And 8 times 12 will give you same number as 3. Okay, 2 times 12. So we will have only 6 numbers from 1 to 6. Okay. So these 6 numbers, 1, 2, 3, 4, 5, and 6 are called least residue. Okay, least residues of 1 times 12, 2 times 12, 3 times 12, 4 times 12, 5 times 12, and 6 times 12. Okay, so either we write 1 times 12, 2 times 12, 3 times 12, 4 times 12, 5 times 12, and 6 times 12 in some orders. Okay. For example, the order of 1 times 12 is 5. Let me use different color. 2 times 12, the remainder of 2 times 12 is 3. Similarly, the remainder 3 times 12 is 1 here. 4 times 12 is 6. 5 times 12 is 4, and then in the last 6 times 12 is 2. So these residues are in different order, okay, not necessarily the same orders, but they are called least residues of these numbers, okay. For example, if you consider this number 12 as a, so 1 times a, 2 times a, 3 times a, and the prime number is 7 here, so there are 6 least residues of that number. So there is a lemma. We are not going into the proof of the lemma, but the statement is very important to prove Fermat's little theorem. Lemma, okay, let me call this lemma as lemma 1. Let P be a prime and a any integer such that P does not divide a, then the least residue of the integers a, 2a, 3a till p minus 1 times a modulo p are a permutation of the integers 1, 2, 3 to p minus 1. Okay, so that's the lemma. Okay, we will use this lemma to prove Fermat's little theorem. So that's our main theorem. We call this as Fermat little theorem. Okay, the statement, let P be a prime and a any integer such that P does not divide a, then a to the power p minus 1 congruent to 1 modulo p. Okay, so that's the statement. Now move to the proof of this result. Okay, we know that the least according to lemma 1. So by lemma 1, the least residues of the integers a, 2a, 3a to p minus 1 times a modulo p are the same as one, two, three, p minus 1 in some order. So their product congruent to modulo p. Okay, let me write a times 2a times 3a times p minus 1 times a is congruent to 1 times 2 times 3 times p minus 1 modulo p. Okay, so definitely, because so if they are least residue, so we can write like that. So we know that we have how many a's here? We have p minus 1 a's here, because the coefficient of a is 1. So from 1 till p minus 1, we have p minus 1 a's which are multiplying here. So we can write a to the power p minus 1, because we have a product of p minus 1 a's. And then we have the product of natural numbers till p minus 1. So if we have a product of natural numbers or natural numbers till p minus 1, so we can write p minus 1 factorial. Okay? And this is congruent to p minus 1 factorial modulo p. We know that p is a prime. So all numbers less than p are relatively prime to p. Okay. So if all numbers which are less than p are relatively prime to p, then their product must be relatively prime to p. Thus, we can write now the GCD of p minus 1 factorial and p is 1. So if the GCD of p minus 1 factorial and p is 1, then we can divide this result by p minus 1. This congruence by p minus 1. So we will have p minus 1, or we can multiply by the inverse of p minus 1 factorial, whatever. So a to the power p minus 1 is congruent to 1 modulo p. So that's the statement of Fermat's little theorem. Okay. So by using Fermat's little theorem, we can find the remainder. We can find whether the number is composite or not, or whether the number is divisible by some numbers. So we can, for example, find the remainder. So we have to find remainder when 2 to the power 24 to the power 1947 is divided by 17. Okay. So when, let me write 17 here. So divided by 17. Okay. So now 24, because if we use Fermat's little theorem here, so A is 24 and P is 17 and P does not divide 24. So it means we can apply Fermat's little theorem. And by using Fermat's little theorem, A to the power A is 24, so better to use 24. So 24 to the power P minus 1, P is 17. So 17 minus 1 is 16, congruent to 1 modulo 17. So it means whenever 24 to the power 16 is divided by 17, then the remainder is 1. Okay. So let me simplify that. So 24 to the power. So we know that 24 to the power 16 is 1. So we break 1947 in such a way that we have the product of 16. Okay. So 1947 can be written as 16 times 121 plus 11. Okay. You can use division algorithm here. Okay. So by using the division algorithm, because 1947 should be divided by 16, so you need to find Q and R such that 1947 can be written as. So this is, for example, N, this is M, this is Q, and this is R. So we just used the division algorithm here. Okay. So 24 to the power 1947 can be written as 1947 can be written as 24 to the power 16 times 12 plus 11. Okay, because this is 1947, and this can also be written as 24 to the power 16 120. We have 121. 16 to the power 121 times 24 to the power 11. Okay. So now use congruent sign here, because we are using the congruence here, because whenever 24 to the power 16 is divided by 17, the remainder is 1 here. So we put 1 here, so 1 to the power 121, now we are using, and then 24 to the power 11 modulo 17. Okay. So this 24, 1 to the power 121 is 1, and 24 to the power 11. Now this 24 can be written in modulo 17 as well. So either you can write negative 10 or plus 7, because the residue class or modulo class for 24 minus 10 and 7 is same. Okay, so 7 to the power 11 modulo 17. Okay, now we have to simplify 7 to the power 11 for modulo 17. So 7 to the power 11. So 11 can be written as 7 to the power 2 n to the power 5 times 7. Okay, and this is congruent to, so 7 squared. 7 squared is 14. 14 in modulus 7. 7 squared is 49. So 49 is negative 2 in modulus 17, because 17 times 3 is 51. So this is 49. So minus 2 in the same class, minus 2 to the power 5 times 7 modulo 17. So this can also be written as minus 2 to the power 5 is 32 and minus 32. Okay, so minus 32 and plus 2 are same, so better to write plus 2, because minus 32 means plus 2 in modulo 17. Okay, because 2 means minus 32. 2 times 17 is 34. Okay, so 34 minus 2 is 32. So 2 times, so minus 2 to the power 5 can be written as 2 times 7 modulo 17, and this is congruent to 14 modulo 17. So the remainder, when 24 to the power 1947 is divided by 17, then the remainder is 14. Okay, move to the different example. Let me give another example. Okay, show that for every integer n to the power 33 minus n is divisible by 15. Good. So it means for any integer, you can put here 2. So 2 to the power 33 minus 2 is divisible by 15. You can put here 3, you can put here 4, you can put here 5, you can put here 9, you can put here 11. 11 to the power 33 minus 11 is divisible by 15. Okay, that's very important. Very good result. Okay, so now how can we prove this result? Okay, we use Fermat's theorem to show n to the power 33 minus n is divisible by 15. First, look at the value n to the power 33 minus n. Okay, this can be factorized by taking n as common. So we will get n to the power 32 minus 1. Okay, so n to the power 32 minus 1 is the factorization of n to the power 33 minus n, and 15 can be factorized as 3 times 5. So this is the prime factorization of 3 and 5. So if 3 divides n, okay, so if 3 divides n, then surely 3 divides the whole product. Okay, if 3 does not divide n, then, so if 3 divides n, then 3, because for to show that 15 divides this expression n to the power 33 minus n, okay, we will show in parts. First, we will show that 3 divides this product, this expression, and then we will show that 5 also divides this expression n to the power 33 minus n. Okay, so because 3 and 5 are prime numbers, and 3 and 5 is the factorization of prime factorization of, or prime decomposition of 15. So if both of the factors are dividing n to the power 33 minus n, it means 15 divides the expression n to the power 33 minus n. Okay, so if 3 divides n, then 3 divides the product n to the power 33 minus 1. Okay, that's done. If 3 does not divide n, then by Fermat's theorem, so here is the application of Fermat's theorem. By Fermat's theorem, n is square, because 3 is a prime number, and which is not dividing n, so n is an integer. Okay, so which is same as a in the Fermat's little theorem. So a to the power p minus 1, so a n to the power 2, it means 3 minus 1, congruent to 1 modulo 3. That's Fermat's little theorem. Okay, so now look at our result, because 3 is not dividing n. 3 does not divide n. Okay, so it means we are proving that 3 divides n to the power 33 minus 1. 32 minus 1. So now n to the power 32 minus 1 is equal to n square to the power 16 minus 1. Okay, so now this is because n square modulo n square congruent to 1 modulo 3. So now we use congruence sign here, and we have 1 here. So 1 to the power 16 minus 1 congruent to 0 modulo 3. Okay, so it means n 32 minus 1 is congruent to 0 modulo 3, so which can also be written as n to the power 32 congruent to, or there is no need to write further, because we are dividing n to the power 32 minus 1, and we are getting remainder is equal to 0. It means thus 3 divides n to the power 32 minus 1. So it means 3. Okay, so this implies 3 divides n times n to the power 32 minus 1. Now for 5, okay, for the other factor 5, so if we will use the similar argument here, so if 5 is dividing n, So it means 5 divides the whole thing. If 5 does not divide n, then so if 5 divides n, then 5 divides the product n times 32, n to the power 32 minus 1. Okay. If 5 does not divide n, then by using Fermat's theorem, by Fermat's little theorem. Actually, we are using little theorem here, so better to write Fermat's little theorem. N to the power, because prime is 5 here and a is n here, so n to the power 5 minus 1 means 4 is congruent to 1 modulo 5. Okay. So now n to the power 32 minus 1, which is equal to n to the power 4 whole power 8 minus 1. So this is congruent to 1 to the power 8 minus 1, and this is congruent to 0 modulo 5. So it means 5 divides n to the power 32 minus 1. So it means either 3 divides n or n to the power 32 minus 1, and 5 either divides n or n to the power 32 minus 1. It means in both the cases, the product of 3 and 5, which is 15, divides n times n to the power 32 minus 1 or n to the power 33 minus n. So thus 15 divides n to the power 33 minus n. That's it. The next thing is linear congruence by using Fermat's little theorem. So we have already studied linear congruences. Okay, so I think we have studied enough things in linear congruences. Although you can also solve linear congruences by Fermat's little theorem. Okay, so I am leaving that thing for you as an assignment, and now move to another result. Okay, let P be a prime and a any positive integer, then a to the power p is congruent to a modulo p. Okay, so this theorem is valid for both of the cases, whether n divides, whether a divides, p divides a, or p does not divide. Okay, so look at the proof. Okay, let me correct one thing. The linear congruence by using Fermat's little theorem is not the part of the assignment, but you can consider that thing as an exercise. Okay, so prove. So suppose P does not divide A, then by Fermat's little theorem, we can write A to the power P minus 1 congruent to 1 modulo P, okay? And this can also be written as A to the power P times A to the power minus 1 is congruent to 1 modulo P, because these integers are in Z modulo P, okay? So all of the integers A to the power P or A to the power P minus 1 or all powers of A belongs to, all integers belong to Z modulo P, okay, or ZP. So ZP is a field. So every non-zero element of P has an inverse. So if we multiply, because A inverse, the inverse of A is A, so we multiply A both the sides, we will get A to the power P here is congruent to A, or let me use two steps here. So A to the power P times A to the power minus 1 times A is congruent to 1 times A times modulo P, or we can write A to the power P is congruent to A modulo P. So this is the case when P does not divide A. Okay, look at the second case. When P divides A, suppose P divides A, okay, then if P completely divides A, then P, whether we write P or we write A, all of them are congruent, 0 modulo P. Okay, so by using a result that we studied in chapter 4, that we can also write, because P, A, 0, all of them are congruent for modulo P. So we can increase powers. So A to the power P is congruent to A modulo P. Okay. So in both of the cases, A to the power P congruent to A modulo P. So that's the result. Okay, now move to the Euler's theorem. Okay. So before going to move Euler's theorem, let me discuss the problem with Fermat's little theorem, because if you look at the Fermat's little theorem, we must have a prime P. Okay. So for example, if we don't have prime, for example, if we have 9, for example, if we have 8 or any composite number, okay, then we can't use Fermat's little theorem. So in that case, we can use Euler's theorem, okay, that is also called Euler's generalization, okay. So before going to the, in that case, Fermat's little theorem will become a corollary of Euler's theorem, or become a very simple function, very simple theorem. So look at the statement of Euler's theorem or Euler's generalization. Euler's theorem. Let m be a positive integer. Let m be a positive integer and any integer with GCD of a and m is 1, then a to the power phi m is congruent to 1 modulo m. So that's the statement. Okay, look at here, because there is no need to be a prime for m. Okay, m could be a composite number. Okay, and look at here. So this phi m is called Euler phi function. Okay, so before going to the proof of Euler's theorem, let me define Euler's phi function. Okay, so this is phi m. Phi m is called Euler okay, Euler's phi function phi m, and how can we define this number? So this number or this function denotes the number of positive integer less than or equal to m and relatively prime to m. For example, if m is 6, so phi 6. So phi 6 means the numbers which are relatively prime to 6. Okay, so 1 is relatively prime to 6, 2 is not, 3 is not, 4 is not relatively prime to 6, but 5 is relatively prime to 6. So there are only two numbers which are relatively prime to 6 and relatively prime to 6 and are less than 6. Okay, and for example, phi 12. Okay, so 1 is relatively prime to 12, 2 is not, 3 is not, 4 is not, 5 is relatively prime, 6 is not, 7 is relatively prime, 8 is not, 9 is not relatively prime, 10 is not relatively prime, 11 is relatively prime to 12. So phi of 12 is 4. Okay, so, and phi of 1 is 1 by definition, because we have only one number 1 which is relatively prime to n. So that's called Euler's phi function. So before moving to the proof of Euler's theorem, let me introduce a lemma. We call it lemma 2. A positive integer p is a prime if and only if Euler phi function of prime p is p minus 1. Okay. For example, if you look at phi of 7, okay, so 1 is relatively prime to 7, 2 is 3, 4, 5, 6. So all numbers less than 7 are relatively prime to 7. So it means 6. Okay. So now we have to prove this result with if and only if condition. So proof. So we consider let P be a prime. Then there are P minus 1 positive integer less than or equal to P are relatively prime to P. So phi of P equals P minus 1. Conversely, because this condition is with if and only if, so we have to show converse as well. So conversely, let P be a positive integer and better to use such that phi of P equals P minus 1. Okay. Okay, we suppose let B, because P is any positive integer, it could be a prime as well, or it could be a composite as well. Okay, so if it is a composite, then any number which is between 1 and P minus 1, okay, can divide P. So let D divides P, where D is any number between 1 and P minus 1, or we can write D is greater than 1 and less than P. Okay. So it means, okay, so it means P is not prime. Okay. Since there are exactly P minus 1 positive integers less than P, okay, and D is one of them. So if D is one of them, then GCD of D and P must not be equal to 1. So phi of P must be less than P minus 1. Okay. So this gives a contradiction. Okay, contradiction, because if there are exactly P minus 1 numbers which are relatively prime to P, okay, and relatively prime to P and less than P, less than or equal to P, so it means GCD of all numbers from 1 to P minus 1 is 1. Okay, but we consider here, because we are not considering P as a prime, so we are considering P as a composite number. So it means there must be a number D which is between 1 and P that divide or greater than 1 and less than P, which divides P. So it means D must be a number between 1 and P that exactly that divides P. So it means the GCD of D and P must not be equal to 1. So if GCD of D and P is not equal to 1, so D must be removed from here. So if any number is removed from here, so the Euler phi function should be less than P minus 1, but it is given here P minus 1. So this is a contradiction. So thus P is not composite, means P must be a prime. Okay, now look at the statement of Euler's theorem again. Let m be a positive integer and a any integer with the GCD of a and m is equal to 1, means a and m are relatively prime or co-prime. Then a to the power phi m is an Euler phi function is congruent to 1 modulo m. Okay. Now this result can be used to find the remainders when m is not a prime. Okay. Okay. Let me solve an example. So we have 245 to the power 1040, and this is divided by 18. So 18 is not prime, definitely. We can find 18 is A here. Okay. Sorry, 18 is M here. So we need to find phi M. So phi 18. So the numbers which are relatively prime to 18. So 1 is relatively prime to 18, 2 is not, 3 is not, 4 is not, 5 is relatively prime, 6 is not, 7 is 8 not, 9 is not, 10 is not, 11 is relatively prime, 12 is not relatively prime, 13 is relatively prime, 14 is not relatively prime, 15 is not, 16 is not, 17 is relatively prime. So how many numbers? 1, 2, 3, 4, 5, 6. So phi of 18 is 6 here. Okay. So A is 245. So this is A. So this A is slightly bigger. Okay. So we can reduce it in modulo 18, because M is 18 here and 245 is a big number. So we can find another number, okay, which is in the same class of 245 modulo 18. So 245, when 245 is divided by 18, so the remainder is 11 modulo 18. Okay, so 18, and now either we find 245 to the power 1040 or 11 to the power 1040. There is no difference because they belong to the same modulo class. Okay, 18, 11 to the power. So in other words, we have to find 1040 to the power 11 is divided. So we are converting this question is divided by 18. Okay, so m is 18 here and a is 11 here. Okay, so by using Fermat's by using Euler's theorem, we can write a to the power phi m congruent to 1 modulo m. So by Euler's theorem, by using Euler's theorem, a to the power phi m, 11 to the power phi 18 is congruent to 1 modulo 18. In other words, 11 to the power 6 is congruent to 1 modulo 18. So it means whenever we have 11 to the power 6, we can write 1, okay, in modulo 18. So now we have 1040 power. So 1040. So we can use division algorithm here. So 1040 can be written as 6 times 173 plus 2. 6 times 173 is 1038, then plus 2. Okay, so this is n, this is m, and this is q, and this is r. Okay, by using division algorithm. So 11 to the power 1040 can be written as 11 to the power 6 to the power 173 plus times 11 to the power 2. Okay. So now we use congruent sign here because we are putting 11 to the power 6 as 1 here. So 1 to the power 173 times 11 square modulo 18. Now it becomes very simple. 11 square is 121 and 121 modulo 18. So if you look at 121 in modulo 18, so this is 13. 13 modulo 18. So remainder is 13. Okay. So by using Euler's theorem, we can find the remainders when divided by the composite integers, but there are some restrictions here as well. Okay. So inshallah, in the next class, we will discuss the number theoretic functions. Okay. Thank you very much.